Next up, we have Pierce Darragh presenting Parsing with Zippers, a Functional Perl.
Hello, thank you for watching my talk. My name is Pierce Darragh, and I'll be walking you through Parsing with Zippers, a functional Perl written by Michael D. Adams and me. So let's get to it. Parsing with Zippers is an extension of the earlier work of parsing with derivatives, which we'll call PWD for short. We address an underlying inefficiency in PWD's algorithm by implementing a new, generalized form of the zipper and using it to manage derivations. Our resulting algorithm is significantly faster than the original PWD implementation, measurably faster than the optimized PWD implementation of Adams et al. 2015, and is only around 100 lines of OCaml code when fully implemented. The primary contribution of parsing with derivatives was to generalize Brzezowski's derivatives from regular expressions to context-free grammars. This is not trivial. The Brzezowski derivative uses two eager algorithms, perfectly fine for regular languages, but not so with CFGs, which have recursion. PWD introduced laziness to fix most of one of those algorithms, and memoization and fixed points for the other. The result is an algorithm that is elegant in its theoretical simplicity, and which can also produce full parse trees instead of only recognizing inputs, as Brzezowski's derivatives do. Let's see a brief example of PWD in action. We start with a grammar consisting of a root concatenation node, shown with the circle-like concatenation operator, that has two children concatenation nodes, each of which has two children token nodes. This grammar parses only the string A, B, C, D. We will attempt to parse that string, shown disassembled in the tokens at the top. We take the first token from the input string, labeling it current. Then we derive over the grammar, beginning at the root node. At each step, a pattern match is run to determine what to do with the current node. The derivative proceeds down the left side of each concatenation node as it attempts to find a token node. Eventually, it finds the first token node, A. When the algorithm comes to a token node, it attempts to match that token to the current token that we are taking the derivative of the grammar with respect to, in this case, also A. Because the tokens match, we replace the token grammar expression with a lambda, indicating a successful parse. Since we have successfully derived the grammar with respect to A, let's proceed and attempt to derive the result with respect to B. Again, we begin our search at the root of the grammar, exploring each node in sequence until we find an unmatched token node. And in this case, the traversal down to the lambda would be thrown away, so I'm only showing the traversal down towards the B node. Because the current token and the found token node matched, we replace the node with a lambda node and return a new grammar. We'll stop the parsing example at this point. The takeaway is that each derivative will start at the root of the previous derivative's result grammar. In this simple example, this only means one extra step. But with a more complex grammar with many layers, it could be very many steps. This is wasted effort. Most often, subsequent derivatives need to essentially resume from wherever the previous derivative left off. The PWD algorithm does not account for this, and so it spends a lot of time on redundant traversals. To avoid this, we'll employ the zipper. The zipper is a functional data structure for navigating trees introduced by Hewitt in 1997. We start with a simple definition for a tree data type consisting of either an item, which is a leaf node, or a section, which is a branch. Next, we introduce the path. A path is essentially a context. It represents the part of the tree which has already been traversed and also keeps track of siblings of the subtree currently being focused on. Last, we have the location, which is really the zipper itself. This is a pair of a path with the focused on subtree, which is generally referred to as the focus of the zipper. To solidify this concept, let's look at a visualization. In this diagram, blue squares represent paths, yellow triangles represent tree nodes, and the red circle is a zipper. The red arrow going down from the zipper is the focus expression, and the black arrow going up points to the path. Let's take a few steps through the tree. We'll begin by going down through the subtree T1. When we go down into a concatenation node, a new node path will be created representing the path back up through that concatenation node. This will be attached to the zipper, which will be focused on the first child of the concatenation node, T2 in this case. The remaining children, T3 and T4, are in the node path's right siblings list. We are not limited to traversing the tree in a specific order. We can immediately move to the right without going in any other direction. Notice that a new node path is constructed, which has T2 as a left sibling of the focus and T4 as a right sibling. If we go down through T3, we will create a new node path, C3, which itself points up to C2. Because T3 had no siblings, the left and right sibling lists in C3 are left empty. Lastly, we can return back up through a path, in this case, C3. When we do this, we could create a new node to replace T3, which is why I've underlined T3 in the diagram at this point. In any case, a new zipper is constructed focusing on the tree node we just traveled through, with a path back to the root as always. This brings us to parsing with zippers, or PWZ for short. We use zippers to save the location where a derivative was successfully taken. By doing this, we eliminate almost all of the retraversals in the original parsing with derivatives algorithm. We use a slightly modified zipper definition compared to the original. For one, we actually call it a zipper in the code instead of a location. We also rename tree to exp, meaning grammar expressions, and path to cxt, meaning contexts. All context constructors end with a capital C to indicate their status. Now, there is a problem with our zipper implementation, which is this. It can't yet handle all context-free grammars. It'll work fine for concatenation and tokens, but that's it. Many CFGs have alternates and cycles, which are part of what makes CFGs so useful. We'll have to improve our zipper if we want to use it for parsing CFGs. First, we'll look at supporting alternates in the grammar. This requires adding an alternate constructor to the exp type, and a corresponding alternate context constructor to the cxt type. Here, we have a simple grammar. The inverted triangle labeled A1 is an alternate node, and T1 and T2 are its children. They should be processed independently of one another. When the zipper moves through the alternate node A1, it splits. We get 2 context nodes and 2 zippers, which is exactly what we wanted. Now the children of an alternate node are handled in a non-deterministic manner. When we eventually traverse back up, possibly modifying either or both of the child nodes in the process, we create a new alternate node for each child. These are handled independently by the algorithm. For non-cyclic grammars, this solution is technically sufficient. However, there are some inefficiencies. Here we have a situation where 3 expressions have been parsed, which all descend to a shared expression T1. There are 3 separate zippers sitting between each of the associated context and this T1 expression. Parsing with the first zipper creates a new context, C4, and a new zipper, Z4, which sits between the new context and the child expression T2. Parsing with the second zipper creates an identical context and zipper, but they are separate from the first ones, and the third zipper will do the same. We now have 3 identical contexts, all labeled C4, and 3 identical zippers, all labeled Z4. This is wasted effort. Not only that, but if we were to add support for cycles at this point, the inefficiency could compound and lead to the number of zippers becoming exponential with respect to the length of the input. We can't have that. Here's the code as we currently have it, but now we'll add memoization. The memoization entries simply take the place of the child contexts within each context type, as well as within the zipper. We now have a memoization table, shown on the left. Although the zippers now actually point upward to memoization entries, I show them here pointing to the associated context for visual simplicity. When zipper Z1 attempts to parse into expression T1, we will add an entry to the memoization table so subsequent derivations do not repeat work. It's important that the table entry is added before descending, or else we may still end up with redundant traversals. When the first zipper, Z1, descends through the expression T1, a new entry is added to the memoization table indexed by a pair consisting of the current input token position, which we will call P here, and the expression. The zipper's context, C1, is added to the parents field. When the derivative is complete, the result field will be populated, and we will continue parsing upwards through the parents. Now, when zipper Z2 attempts to parse through expression T1, it first checks the memoization table. If the current input token position is still P, then the lookup in the table will succeed. Instead of doing any additional processing, Z2 will simply add its current context, C2, to the parents field. The last zipper, Z3, will do the same. When the child zipper Z4 eventually returns from parsing through the T2 expression and ascends up through the context C4, it will split again to return the computed result to each of the parent contexts C1, C2, and C3. By using this memoization table, we have avoided creating redundant zippers when traversing down the grammar. But what happens when we instead traverse up? Here's an example where a zipper is focused on an alternate which has not been parsed yet, so it has no entry in the memoization table. The way the algorithm works at this point causes 2 new zippers to be spawned, each pointing to a new Alt-C context node. Note that both contexts, C2 and C3, point to the same memoization table entry for the A1 alternate expression that we just passed through. Let's say zipper Z2 does its work first and returns up through context C2. A new alt node is constructed, A2. This is added to the result field of the old alternate node A1's memoization table entry. When the second child zipper, Z3, passes up through context C3, it also creates a new alt node, A3. This node is also added to A1's result field. 2 alternate nodes have been created, and each has spawned a zipper that will navigate up through parent context C1. This is inefficient, and, similar to the problem with unshared expressions, this situation can lead to an exponential blowup in the number of zippers spawned when deriving over a cyclic grammar. To address this, we will adjust our memoization code to also memoize contexts in addition to expressions. Because the situation only arises for alternate nodes, we simply extend the alt constructor to have a mutable list of child expressions. This will allow us to incrementally update a constructed alt node's list of children as new zippers return up through the tree. We also now only need a single expression to be saved in the result field of the memoization entry. Let's see how it works. We start back at this point, where a zipper has just passed up through an alt-C alternate context and created a new alternate node, A2. The node is added as the lone result in the memoization table. When the second zipper moves up in the tree, it simply modifies the existing A2 node. Now, there is only one zipper created above the newly constructed alternate node, and we have avoided the potential exponential behavior we would have had earlier. While adding memoization to reduce inefficiencies, I mentioned some concerns about a hypothetical future where we support cyclic grammars. Have no fear, the time has come to handle cycles. And behold, they are handled already. Where recursive descent parsers face a dilemma in choosing how many times to descend into a left recursion, we sidestep the issue entirely. Our memoization strategy automatically converts cycles in the grammar into cycles in the contexts. This allows us to postpone making any choices until further parsing reveals how many repetitions are actually needed. The diagramming for this is a bit complex, so I suggest reading section 7 of our paper for a more detailed explanation. And with that, the fundamental theory of our algorithm is laid out, but there remains one more advancement to discuss prior to looking at the evaluation. We can actually completely eliminate the memoization tables, and I'll show why. All our memoizations are indexed by the current input position, but we parse the input tokens sequentially, so there is never a need to maintain old entries. We eliminate the position as an index, and instead make two fields in the table entry to denote the start and end positions corresponding to the successful parse. However, since this table is now indexed only by an expression, we can actually eliminate it entirely and simply put a memoization entry inside each expression automatically. Here's the code as it existed with the memoization table. And here is the code which eliminates memoization tables. We now have a new definition of EXP which contains a memoization record, and an EXP prime, which was previously called EXP. The memoization entries now record the start and end positions associated with successful parses, allowing the algorithm to quickly discern whether an entry has grown stale. And with that, the work is done. Let's briefly look at our performance evaluation. We ran parsing with zippers over the Python 3.4.3 standard library and compared the results to a few other parsers. Parsing with derivatives from Might et al. 2011, optimized parsing with derivatives from Adams et al. 2016, Menhir, an LRK parser generator for OCaml, and Dipgen, a GLR parser generator for OCaml. The parsing with derivatives implementations had to be ported from Racket to OCaml, and Menhir's LRK limitations required that we reformulate some of the Python grammar to avoid potential ambiguities that might distort our comparisons. We ran the benchmarks on a DigitalOcean droplet with a dedicated CPU to ensure we did not introduce any sources of invalidity due to other tasks. The results show that parsing with zippers significantly outperforms the original parsing with derivatives algorithm, and even outperforms the optimized version of PWD that relies on many low-level tunings and adjustments to the algorithm. Although PWZ does not surpass the parser generators in our tests, we believe our result to be significant because of the simplicity of the algorithm. At only around 100 lines of code, parsing with zippers is simple enough to be written by hand, and yet is fairly competitive as long as performance is not absolutely crucial. Additionally, we claim parsing with zippers can handle all context-free grammars, even with left recursion and ambiguities, which Menhir cannot do. So, we've introduced parsing with zippers, a new general parsing algorithm that is simple to implement yet provides surprisingly good performance. Where parsing with derivatives generalize the Brzezowski derivative from regular expressions to context-free grammars, we have generalized the zipper from tree structures to context-free grammars. We also consider asymptotic complexity, other divergences from PWD, and a few more points in the discussion and evaluation sections of the paper, which I would encourage you to read if you have further questions that I did not address. I hope you have enjoyed this presentation of Parsing with Zippers, a functional Perl by Pierce Dara, that's me, and Michael D. Adams. Please feel free to contact us if you have any additional questions or comments. Thank you.
Thanks very much, Pierce. In the New York time band, the authors are now available for question and answer. I'm afraid not in the Asia time band.